If it is recording. Yes, it is recording now. Fine. Yeah. Okay. So it's quite a low turnout today. I don't know why. Let's wait. Let's hope some people join. Anyway, so yeah, as always, this is so let's start. As always, we start with quick introductions. So this course is analog VLSI design. This course is analog VLSI design. It's an NPTEL massive open online course, or MOOC in short. So the instructor for this course is Dr. Iman Mandal. He's an assistant professor in the electrical engineering department at IIT Kanpur. Uh, I am the tutor for this course and hold these discussion sessions on Tuesdays 6 p.m. to 8 p.m. My name is Mayank Anupam. I am a PhD student in the Department of Electrical Engineering at IIT Kanpur. Okay. So today in our discussion, we will be looking at the things that were covered, the topics that were covered in the 11th week, 11th week of the course. So in this week 11, the topics that were covered are briefly summarized here. The headings of those topics are written here. So we saw basically in the week 10 we looked basically differential amplifier was introduced, right? With differential amplifier with a current mirror load was introduced, and today, sorry, not today, but in week 11, the instructor delved into a new concept, which is very important for differential amplifiers, which is called the common mode rejection ratio. So it's a very important topic, as the name of a differential amplifier suggests. It should only be sensitive to the difference of signals that is applied at its input, and it should ideally only amplify the difference of two signals and not the common mode, not signals which are common to both the inputs, right? So that is why something which is very important for a differential amplifier. Common mode rejection ratio. So we looked at it. We tried to quantify the common mode rejection ratio using some equation, this thing, some equations and all. We found out how much common mode rejection ratio we can expect in the differential amplifier which we have learnt about. We saw the key parameters which affect the common mode rejection ratio in the differential amplifier which we saw. Okay, we also saw what happens if if you have a current source at the bottom of an amplifier versus if you don't have a current source, right? We saw all that. We also saw how putting a current mirror load at the top of a differential amplifier affects the common mode rejection ratio, right? All those things we saw. We saw yet another important measure or metric of metric in a differential amplifier, which is called input common mode range, right? So I hope you understood this. Input common mode is nothing but simply it simply means that how much common mode variation I can have in the at the input. How much common mode can I tolerate at the input? So input common mode can vary, right? It depends upon so input common mode can vary in general, and because of that, your amplifier characteristics should not change a lot. They will change definitely, but they should not change a lot. So and also the most important thing is that with the change in input common mode, the amplifier should still be in saturation, and also that those things actually uh, basically define the input common mode range, constrain the input common mode range. What has happened? Yeah. So these are the two important things. Okay. Now we also learned about negative feedback. So I hope negative feedback is something which you are now comfortable with, at least in principle. You understand what is negative feedback, right? Because I also explained it once in the very first or second session, and it was also explained by the instructor in the week 10, I think, and also in week 11. So yeah, differential amplifier negative feedback, which we saw, right? Negative feedback thing. And we also learned about a new thing called a loop gain, right? What is a loop gain and feedback factor? All those things we saw. After that, we came to we evolved, the discussion evolved, and we came across a new kind of amplifier which is called two-stage amplifier. So we also learned about this. We saw why it is important, why it is required, and all those things we saw. So before proceeding with the questions and all, I want to ask you, is there any doubt in the conceptual level, at least, the topics that we have discussed?
Sir, good evening, sir.
Yeah, good evening.
Sir, regarding the CMRR value,
Okay.
instructor sir has used the current ratios and got some GM or not like that. But if we are using the uh, differential gain and common mode gain, we are getting the result as R naught, sir.
Okay, so I'll have to look into that. I don't know. I have not actually seen exactly. Uh, I've not actually gone through the PDF myself, so I'll have to look at it. All right.
Sir,
Okay, let's do that quickly here. So
their differential gain was derived as GMRL by 2, and common mode gain was derived as GMRL by 2R.
which page can you tell me? Okay, CMRR here,
Yes, CMRR value, sir.
GMR not. This is the one, right?
CMRR.
And this one, na?
Yes, sir, GMR not. There it is GMR not. Instructor sir has taken the current ratios, I think. But if you see that in the same notes, the differential gain is GMRL by 2.
Okay, let's try to understand this. Yes, he has taken the current ratios.
Yes,
Yes,
current ratios.
yes, it is the
Sir
current
has
ratio
taken current
that he has
ratios.
taken.
If you see the differential gain, which is in the slides itself, this notes itself.
Differential gain is, yeah, differential gain is for this is what? GM times
Or not.
differential gain is GM times RL, right? GM by 2 times RL, isn't it?
GMRL by 2
By 2, right?
by 2,
That is
and
the differential gain.
differential gain
Common mode gain will be, how much will be the common mode gain? So basically,
GMRL by 2 R naught.
so the common mode, what is the common mode GM, by the way, first? Tell me that.
GMRL by 2 R naught.
GM RL by 2 or not? That is definitely not correct, right? How can that be the common mode gain?
Uh,
That is incorrect. No, this is dimensionally incorrect. How can that be incorrect? How can that be the common mode gain? Where are you saying that is written?
is written in the this notes also, sir.
Where is that? I am sliding. Okay, so tell me where I should stop. I'll
Uh,
stop there.
no, no, it is in the starting itself, not here, sir. The starting
Okay,
itself.
let's go to the start itself. Okay,
It's from page number 5, I think.
Yes,
page
yes.
number 5. Yeah,
This
it
is
is.
ACM.
Oh, no,
GMRL by 2
it
R
is
naught.
wrong. It is not correct. It is incorrect. It should be, I mean, this is dimensionally incorrect. Okay,
Okay.
you understand? No, this is dimensionally incorrect. This is not correct. The gain cannot be this much. Gain, you see, GM times RL is dimensionally, it has no dimension, right? Divide by 2 R naught, it becomes, the dimension becomes overall of conductance. Okay,
Connect. Yes, yes.
so this is dimensionally incorrect. So some mistake has been done in the calculation. Something might have been missed.
So I initially checked with the ratios of gains. then I
Ah,
got
the
different answer
actual thing
from.
is that you should check with the gains ratio only. Okay. The
Okay.
current gain is here. It might actually you should check with the current gain only. No, no, no. You should check actual gain only. Okay. It's
Yes, sir.
defined as actual gain only.
A differential
Voltage
by
gain.
ACM.
Yes. It's not the current gain that is defined. It is the actual gain. Okay. And the output resistance differs.
So,
Okay. When you have
which one we should GMR? We should consider GMR not only, sir.
no,
Which
no,
is
that is not no, no. You should uh, you should calculate it yourself. Here he has taken the current ratios. Okay. But the correct way to do it is the voltage ratios. That is what you should do. Voltage gain ratios. Okay, not current
yes.
gain ratios. You should take voltage gain ratios. Getting my point?
So what is the correct?
It is voltage gain ratio that is the correct. A div by ACM. Okay.
Okay, okay. What should be the result?
Correct value. Result.
Well,
Oh,
result.
that we have to calculate and see, right? So here
Okay.
see, as you already saw, this is fine, right? Differential gain is fine. GM times R RL, right? GM by 2 times RL. That is differential gain.
Yes.
Let's do that. Yeah, cannot write it here. Okay, anyway, so I would tell you how it is. See, yeah, good. Here I can write. I can write. Where is that writing thing? Okay, 1 second. Let's do it here ourselves. Uh, this is what? This is a CMRR, CMRR, right? CMRR in differential amplifier. Okay, so we already saw that differential gain is what? What is differential gain? Okay, so first thing is that
GMRL by 2.
yeah, right. Yes, so we already saw that the differential gain is how much. This is let's get red. Differential gain is GM by 2 times RL. This is differential gain. Okay. And common for common mode gain, what do we need to do? So common mode gain for that, uh, first you have to write the common mode picture. See, right? First you have to find out how will the circuit look like in the common mode, isn't it? So take a copy of this. Okay, paste it here. Put this way, paste it here, right? And then we'll have to find out how the circuit would look like in the common mode picture. So this will be replaced by its resistor, right? R naught, isn't it? And both these places we have to apply a delta V, which will be exactly same, correct? Isn't it? And then we'll have to see how much is the gain that we would expect because of this, isn't it? Are you getting my point?
Mayank, just a question.
Yeah.
What is that VIM and VIP in the app? Yeah,
No,
first figure.
this is basically the small signal, isn't it?
So if it is, let's say, 100 millivolt,
Uh,
so that is 100 millivolt,
no, no. VCM
or
is,
it
let's
is
say VCM is the bias voltage, isn't it?
right, right.
And VIP is the small sinusoidals or whatever signal that you are applying here, small incremental voltage that you are applying here.
Yeah, so that is my question actually. Let's say we are applying 100 millivolt sinusoidal signal there.
Yes.
Okay.
Yeah.
So in the lecture, professor told us that it is V1 plus V2 divided by 2, and another is minus V1 minus V2 divided by 2 we should take.
True, true. That I understand. That
So
he split the voltages into common mode and differential
which
mode. I am not
voltage?
doing that.
100 millivolt?
See, okay, let me explain this. See, here I have not made any distinction. Okay, this VIP and VIM are not strictly differential. If I had written it in this manner that the voltage here is VCM plus delta V and the voltage here is VCM minus delta V, then I will then that means that uh, above the common, this is the bias voltage. VCM is always the bias voltage. Okay, so for that only I have written it in capitals. If you can see, VCM is
No,
the
that
bias
I
voltage here.
understand.
Huh?
That
So
I understand. So
this is
that
bias
is
voltage.
complete. If you just
One second, let me finish. So this is VCM plus delta V if I write like this. It means that this delta V now is differential. But let's say if I write it in this manner, VCM or the manner that I just wrote here, VCM plus VIP, VCM plus VIM. Okay. So when I write it in this manner, it means that there is a bias voltage VCM and there is some signal VIP and VIM at the inputs. Okay. Now these signals may not be fully differential. Okay. They might have some common mode component and differential component. If I want to split it further, how will I do that? If I want to split it further into common mode and differential mode, I'll have to do it in this manner that V common mode small signal, okay, will look something like this. So this will look something like this: VIP plus VIM divided by 2 and VDIF will look something of this kind. It will be VIP minus VIM by 2, and when I write it in this manner, the signal again at the input I can modify it in this way that the bias voltage is VCM still, okay, and but instead of with this there is a common mode voltage which is called VCM small letter, and there is a differential voltage at this node which is called VDIF, okay, and at this terminal I can write it VCM plus VCM small minus VDIF. Getting my
okay,
point now?
understood. Understood.
Yeah, this is how it is. So here I have not made any distinction right now. Okay, VIB and VIM are just some signals which may have some common component to it. Okay, so that's why
Sorry,
yeah.
V difference is VIP minus VM by 2 or VIP minus VI.
No, it
V
is
difference.
differential by 2. Okay. Yes. So now, yeah, now I have to find out. So instead of delta V, let's call it VCM only, so that it will relatively makes things easier. If this is VCM. By the way, when I write it, everything in small letter, it means I'm talking about the small signal sinusoid, small signal model. Okay. These are small signal voltages. Please be very careful with that. And in the small signal picture, this VDD is what? Is not there, right? There will be ground, isn't it? Okay. Now tell me what will be the gain from VCM. So basically, what is the common mode gain in this case? The formula will be, common mode gain formula will be VOM plus VOP divided by 2 divided by the input, right? Input common mode. Basically, this is VCM plus VCM divided by 2. Or in other words, it will be VOM plus VOP divided by 2 times VCM. Right? This is a common mode gain. Are you getting my point? I would like some yes or no, because otherwise I don't know if you understood it or not. So
So ACM equals to VOM plus VOP by 2.
by 2,
VOP is also what is VOP? VOP is output. Okay.
yeah, two outputs, right? Differential.
Okay.
So there are two terminals, two outputs. But now let me ask you something. If both so you know that these M1 and M2, both these transistors are identical, right?
Yes.
Yeah. Now also this RL and RL both are identical. Okay. You have applied the same signal at the input VCM and VCM. So what do you think should happen at VOM and VOP? I mean, should they be identical or should they be different? What should happen? Tell me. I mean,
Yeah,
VOP. Yes.
depending on which terminal has higher or lower voltages, that
No,
should
no,
be.
no. But that's what. I have applied same voltage here. VCM, VCM. So same. This is exactly same. So tell me what will happen to VOP and VOM. Will they be same? Will they be
I,
different?
yeah, they will be same, I think.
Yes, they will be same, right? So
Mhm.
VOM and VOP are essentially the same thing, right? So if I try to modify it, how will this look like? This will be VOM or VOP, right? Divided by VCM, right? That will be the gain, correct? Common mode gain, ACM, isn't it? So now tell me what will be the common mode gain here. If I apply a signal here, VCM here, what will be the common gain? What do you know about it? How do you find out the gain? At this point, let me explain to you something about common mode circuit. So this is a common mode picture, okay? In the common mode picture, you can see that this is a fully differential picture, by the way, right?
Yes.
Okay. So here, if you can see, uh, if this is a axis, okay, you can see everything that is left and right to it, they are exactly identical, right? They are like mirror images of each other, isn't it? So for R naught, let's split R naught into two parallel resistors. Okay, sorry. So let's make it. So if I split R naught into two parallel resistors, so how will they look like? Two R naught, right? Individually.
Sure.
Okay. Now tell me something. These two look like mirror images of each other, isn't it? Right?
Yes.
So if I mean with that in mind, and we know that mm, so okay. So tell me another thing. So if the same voltage is applied this place and this place and this place at both the terminals, if the same voltage is applied, what do you expect to be the voltage at this point and this point?
Could you repeat again?
If the same input is applied at both, same voltage is applied at both the inputs, what do you expect to be the voltages at the this terminal and this place, both these places? It will be same, right?
Yes.
Even if I remove it, this connection here, will they be same or not?
Same.
Correct. So this connection is not mandatory, at least in this condition, for both the voltages to be same, right? For both the node voltages to be same, right? They will be same irrespective of the connection, this connection, right? So I'll just remove the connection here. Similarly, the voltage here, okay, sorry, the voltage at this place is what? It's ground, right? Here also it is ground. So I can simply remove this connection and I can push this ground one here and one ground to be here, right? I can do that, nah? Can I do that or not?
Yes.
Yes, good. So now you can see that both the circuits are identical, right? And we already saw that ACM or common mode gain is what? It is simply VOM by VCM, right? Or other way, you can also say it is VOP by VCM, right? This is what we saw here. This is correct?
Yes.
Yes. So tell me what will be the gain now? Now you can find it out, right? It's very easy now. It's a simple one transistor circuit. You only need to look at this you only need to look at this guy here to find out what is the common mode gain. So tell me quickly, what will be the common mode gain here? What will be the common mode gain here? Quick, what will be the common mode gain here? Come on, guys. How do you find gain?
Output voltage divided by input voltage.
Output voltage divided by input voltage. So that is anyway written here. VOM by VCM. So what is that? How do you find that? You remember, right? First you find out what is the short circuit current, right? And then you find out what is the output resistance. You multiply both of them, right? I mean, is it correct or not? So gain ACM is equal to VOM by VCM. It is time for you to revise, okay? So you guys should revise this thing. So this is basically your common mode gain. And how will you find it out? So gain can be found out in this manner. So first you find out what is the, so it is basically short circuit current, or rather short circuit current into output, that is VOM here, okay, and this should be multiplied with the output resistance looking into the output. So what will be the short circuit current because of a small VCM here? So this is the picture. This is RL. Okay. When I say short circuit current, it means that I'm simply shorting this guy right here. Okay. And please mind it that it is shorted in the incremental sense only. It is not like short I've connected to ground. It is incrementally shorted, which means that this is not actually shorted to ground but incrementally shorted to ground. Okay, so I hope that distinction is clear to you because this was also explained in the lectures. If I want to short it, I mean incrementally short means this node here will be connected to a voltage, simple voltage source, which will be some VCM. Okay, bias voltage basically at this node. So in this incremental picture it is shorted to ground, and here we have applied a small VCM, right? And this is what, this is 2R naught. So tell me, if this transistor has GM, right? So what will be the current ISC that flows out of this, or rather uh, here? What will be the current here? What will be the current here? What will be the current in this polarity? Tell me. Okay, so for finding the current, what do you need to find? Current should be what? GM times VCM minus, if we call this node as Vx, right? So the VCM minus Vx, right? This will be our ISC, right? Tell me something. Is there any current that is going to flow into this resistor RL? Can any current flow into this resistor RL?
No.
No, right? So this RL is as good as not being there, right? So just ignore this RL. Now, whatever current is going to flow through this transistor, it's only going to flow through what? It's only going to
The
go
short
to ground.
circuit path. Short
Yes,
circuit.
correct, exactly. So please be mindful of the fact that there should be a minus sign here, okay? Because Gm times Vcm minus Vx, this current flows in this manner. The current polarity that I have taken here is this, right? Okay, now find, so the challenge is what? Finding Vx. So what is Vx? It is quick. What is Vx in terms of ISC? It is ISC times 2R naught, right?
One.
Yes.
Good. So what is then ISC is equal to minus Gm times VCM minus ISC times 2R naught. So what will this look, how will this look like? Did I make a mistake somewhere? Yeah, it should be minus ISC, okay? Again, because the polarity of ISC is in this manner and the current is going to flow here, right? So it's a minus sign here. So it will be plus here. So tell me, how will this look like? So ISC 1 plus GM 2 GM R naught is equal to GM times VCM. So what will be your ISC minus GM times VCM divided by 1 plus 2 GM times R naught. Okay, this is your ISC. You can also remember this result, right? Because this is a very famous configuration where you have the source which is terminated with some resistance. So what is the ISC in that condition? So it is GM divided by 1 plus 2 GM R naught. Okay, or rather GM times whatever is the resistance that you have terminated it with. Fine. So this is ISC, and what is the output resistance? What is the output resistance? So this should not take much time, right? This is very easy because you've already done this plenty of times. This is RL, this is R naught, 2 R naught, this is GM. This you will have to ground, right? And here you have to find out what is the R out. Yeah, tell me, what kind of circuit is this? I mean, why are you so silent today? This is very easy, right? This you have done plenty of times. Someone please speak up. What is the output resistance to this way? So this can be written, visualized in this manner, right? Huh. So this can be visualized in this manner. So for finding R out, we know that we have to apply a test voltage, correct? V test, and then we have to find out what is the I test. Yeah, we have to find out what is the I test. So tell me this I test here, some part of it will split here and some part of it will split here, right? This I test. Is that understood?
Yes.
Yes. So it means that whenever there is split in the I test, I mean in the current, we know that this means that something is parallel to something, right? Also, it is very easy to see here that this RL resistor is parallel to this guy because you see what are the two terminals of RL resistor? The two terminals, one terminal is this one and other terminal is this one, right? And what are the two terminals of this complete guy? This is also one terminal is what? This one, and one terminal is
Yes.
ground, right?
Ground.
Yeah, so both the terminals are common for both of these, right? So this means that
Yes.
these two guys are in parallel to each other. Hmm.
Yes.
So so this makes our job easier. We just have to now find out what is the resistance looking here, R out 1, and looking here, R out 2, and simply make and simply put them in parallel, isn't it? So tell me what is R
Yes.
out 1. So overall R out, or that is equal to V test by I test, will be what? R out 1 parallel R out 2. So tell me what
Two.
will be R out 1, and this I want very quick answer from you because this is a very common architecture. What is R out 1?
1 upon
RL,
GM.
1 upon Gm?
RL,
Come again? What is R out
Uh,
1? Hmm. So basically for finding R out 1, you assume that there is some output resistance here, okay? Let's say this is RO1. Let's call this RO1, okay? Corresponding to M1. So this is RO1. Now tell me what is this? You remember this, right? This is cascoding kind of, right? What is R out 1?
GMRO1 plus 2R naught
GMRO1 into
plus
RO2
uh,
RO2, right? Plus RO1 plus 2 RO2,
2R naught.
right?
Yes.
Yes. Now, since you are not given any R out, at least in the so if let's say if you assume that these two transistors have infinite output resistance, which means that this guy will simply become infinity, right? R out one will become infinity because RO one will become infinity. Correct?
Yes.
Yes. So you can assume that the overall R out will be then. So what this will be? So this guy tends to infinity. So this guy also tends to infinity. So what is R out in that case? Simply R out 2, right?
R out to yes.
Which is simply RL. Correct?
R.
Yeah. So now tell me
Yes.
what is the IS what is the total short circuit sorry, what is the common mode gain in that case? So common mode gain is what? It was ISC times R out, which is now minus GM uh, sorry, it is not just ISC, it is common mode. So it's not just so short circuit current. Uh, so it will be so ISC divided by VCM. Short circuit current gain, you can say, not current gain. It's not correct. Short circuit current into the output V1 divided by its input voltage. Okay. So this is minus GM divided by 1 plus 2 GM R naught, and this is what RL. So what is common mode gain? Minus GM times RL divided by 1 plus 2 GM times R naught. This is your common mode gain, okay? And what was differential gain? What was differential gain? Minus GM by 2 times RL, right? Correct now. So what will be the overall this thing? Now what will be the this thing? CMRR. What will the CMRR? A diff divided by ACM. What will that be? Minus GM times RL divided by 2 divided by minus GM RL divided by 1 plus 2 GM RL. Sorry, R naught. So this cancel each other. So this becomes how much? And this will be plus. So this will be 1 plus 2 GM R naught divided by 2. How much will this be? 1 by 2 plus GM times R naught. So in general, GM R naught will be much larger than 1 by 2. So we can ignore this. So this will be approximately GM times R naught. So is that understood? So who asked this question, by the way?
Yes,
Suba, right?
yes.
Yes. So
Understood, sir.
got it
Understood.
right. Now the
Yes, sir.
common mode rejection ratio is understood.
Yes.
Yes. So this is what it is. So it is correct actually. Common mode GM times R naught here. Fine. But the correct way to do it is not in terms of current, but the voltage itself. The voltage gain is the one that you should look for, and not the current itself. Current gain. You should find out the total thing, and then you should do it. Otherwise, you might end up making a mistake. Okay. Fine. Now let's see. Some people have commented something. So Abhishek has a comment here. Why we calculate separately for VCM and VD in input? So Abhishek, are you there? Abhishek, are you there? I'm sorry, I cannot hear you. Are you there, Abhishek? Okay, fine. So yeah, so I was saying that yeah. So basically, the reason that we do it separately in basically we calculate separately for common mode and differential mode is because we want to exactly find out how our circuit behaves for common mode and differential signals, because this is a differential amplifier after all, right? So differential amplifier is supposed to only amplify the difference of two signals and not the common mode of two signals, right? If the difference is something which should be sensed by the differential amplifier and that should be amplified. Okay, so that is why we try to do it in that manner, because we want to separately understand how the circuit actually basically behaves for common mode and the differential mode. So does that answer your question?
Yes, sir.
Yeah, thank you. Yeah, so Nilesh has commented, sir, I was wondering if you could talk about the exam pattern, the kind of question that will be asked. Will they be similar to those asked in week assignment? So would we have week wise questions, theory questions as well? Thank you. So the thing is, Nilesh, is that so Nilesh, by the way, are you there? Nilesh, are you there?
Yes, sir. Yes, sir. I'm
Yeah.
here.
So yeah, Nilesh, the thing is that I actually don't know. Okay, because I don't look after the administration of this course. I only come here for the sessions. So I frankly I don't have an idea how will the questions be. Okay, but the thing is that if you are regular with the course and you have actually worked on the assignments, I don't think you should have any problem, because the questions more or less are more likely to be very similar to the ones that were asked in the assignments. I hope so, but frankly speaking, I don't have an idea. Okay,
Okay, sir. Thank you, sir.
yeah, welcome. So now coming to the problem at hand. So I mean I today this week I don't have much to discuss, okay, because I mean these are all something which are uh, basically add-ons to the previous this thing. This is not basically okay. One second. Ah, so this whatever is taught in this week, the main portion of that was common mode rejection ratio, and that is something which I discussed right now. Okay, in the previous so here is something which I discussed, common mode rejection ratio. So I hope this is understood. So if this is understood, I don't think there is much to discuss in the problem wise also. Problems also are very similar to the previous problems which you have already seen, just that you have to now simply look at the common mode also, right? So so I don't think I have much today, so I'll just try to wrap it up quickly with with one or two questions which I have. The question here is, yeah, so this is something which I left it last time, right? I wanted you to do it. Fifth part of this question. So did you try it? Anyone? So if you don't try it, I will not explain it. If you have tried, I will explain it. Did you try it?
No.
Yeah. So that answers the question. I am not going to talk about it if you have not tried it at all. You should have, because this is something which I wanted you to learn. If you had done it, you would have understood it. So it's a very qualitative question, by the way. It would not have taken much of your time. Anyway, I just try to speak about it a little bit. So I asked, so this is a differential amplifier, right? This is a differential amplifier with a tail current source here. And this question is very easy because this tail current source is ideal. This has infinite output resistance. So this makes our job very easy. And all the transistors also have infinite output resistance that is something which you can assume. So channel modulation is something which you can neglect here. So I asked the question, what happens to the total current This is I. So total current that is going to flow in this branch and this branch will be what? Will be some bias current I1 plus small I1, right? Small I1 is the small signal thing. Total current will be the bias current plus small signal current, and in the same way in the second branch also. So what happens to the total current when V2 is equal to minus V1 and V1 is equal to 10 millivolts sin omega t is applied at the input. So I simply wanted to ask is if I give a differential input here, V1 is equal to minus, so V2 is equal to minus V1, right? So it's a fully differential input, right? It's a fully differential input, and I wanted you to find out what happens to the total current I1 plus small I1 and I2 plus small I2. So okay, tell me something. What is the total current I1 plus I2? What is the total current I1 plus I2 at any point of time?
4 milliamp.
Yeah, 4 milliampere, because this is something which is constrained by the current source here. So total current cannot change. So but you know that when you increase the voltage here and decrease the voltage here, basically when you have differential signals, that is if it is plus 10 millivolt here and if it is minus 10 millivolt here, the voltages at these two nodes are going to respond to it, right? Voltages are going to respond. So if this is plus 10 millivolt, this voltage will go down slightly, and if it is minus 10 millivolt, this voltage will increase slightly, right? So if this is happening, you can clearly understand that the voltage and currents are related to each other, right? So if the voltage here is increasing, it means what? The current I2 that was flowing is what? Is
Decreasing.
decreasing, exactly. Yeah, so current I2 is decreasing. Current I2 has decreased slightly, and here the voltage has decreased, which means that current I1 has increased. Correct?
Yes.
Yes. So basically, what I wanted you to learn was how the current behaves when when you apply a differential voltage at the input. So the current also is differential. When the voltage is differential at the input, the current is also differential. Okay. Please note that the current here and here will be exactly opposite to each other. The small signal current, this I1, sorry, this small I1 and this small I2 will be exactly opposite of each other in the same manner that V2 is related to V1. So I2 will be minus I1. Okay, this small I2
Okay.
will be equal to minus of small I1, and the total sum of the current will always be equal to 4 milliampere. So tell me, do you expect something should happen if the voltage here instead of 10 millivolt, if let's say I increase it to 100 millivolt, what should happen? What should happen to the current?
It
If
will be
it's
same.
no, I mean it will be same, but the currents, will they increase or decrease, or what will happen? I have increased the voltage, so what should happen to the currents here? Earlier there was some small signal current I1 and I2. Now I have increased the voltages here from 10 to 100 millivolts. So now what should happen to I1 and I2, small I1 and I2?
I1 will increase.
Yes, I1 will further increase, right? I1 will become even larger and I2 will become even smaller, isn't it? With 100 millivolt. So which means that this current is increasing and this current is further reducing. Okay, but the total current remains same. So what is happening is that this current is being steered into this branch, and so more and more of this current is being steered into this branch compared to this branch as the voltage is increasing. V1 is increasing. Are you understanding the point here?
Yes.
Yeah. Now you expect that there will be a point where if you increase the voltage at this node further, all the current will be completely flowing through the first branch only, M1 only, right? and nothing will flow
Yes.
through M2. There should be a point, right?
Yes.
Yeah, so this is basically current steering. Okay, I mean this is a very important concept, and it's heavily used in wireline circuits and all. Okay, um, so there's something just to
What
motivate you.
circuit?
Wireline circuit, something which is so you transfer your files from computer to your mobile data, right? Mobile to computer and all. They are connected using a cable. So wireline circuits, wireline communication. There is wireless
Your
communication.
voice is breaking.
Hello, hello. Is this audible? Is it better
Yes.
now?
Yeah.
Yeah, so I was saying there are two types of communication, right? So wireless communication is something where we use our mobile phone, right? Our mobile phone is
Mhm.
wireless, and there is something called as a wireline communication, wherein the transfer of data will happen through a cable, and that is and the example for which is what, when you transfer files from your computer to your mobile phone, or inside the computer also there is multiple data which is being transferred from part of the one part of the basically computer to other part of the computer. So they are all wireline transfer, isn't it? So that is wireline communication. So this is a current steering is a concept which is very widely used in wireline communications. Okay, I mean there is an application of this current steering thing. So this is what I wanted you to appreciate. If you start applying voltages here and there, current will be steered here and there. Fine.
Yes.
Yeah, good. So after this is the example. This is a question that is very similar to the one that you have in your assignment. So first, tell me something. So you can quickly find out what is the quiescent voltages and current, right? That is not a big task here. So quiescent voltage and current you can find out, right?
Yes.
Yes. Now, the difference that I've taken here is that from the case of the question, from the case of the assignment is this particular this thing. So I'm sorry. Uh, are you guys with me? I'm sorry. There was some problem at my end. Am I audible now?
Yes.
Yeah. There was some problem at my end. Something happened abruptly. So one second. Let me take care of that. My computer suddenly switched off. Let me try to take. Yeah. Yeah. Uh, good. So am I audible now? There should be some voice. There will be some noise, but still, am I audible?
Yes, yes, you're right.
Yes.
Good. So let me first again start sharing the screen. Huh. As I was saying, the difference here is that in the assignment you were asked to assume that IB is basically ideal current source, right? That is, there is no output resistance with IB associated with IB, right? There is no output. I mean, output resistance is infinite. But in this case, I want you to also take two cases wherein IB is an ideal current source and IB also has some R out, which is, let's say, 20 kilo ohm R out. So what will happen in that condition? So what do you expect? So if IB is an ideal current source and if you have applied 3.9 volt and 4.3 volts, what is going to happen? So V1 is what? As I said earlier, V1 is what? VCM is VCM plus some small V1. Okay. And V2 is what? VCM plus some small V2. So as was done in the previous this thing, just before this I discussed a lot on this. So this V1 and V2 are in general voltages, okay, small signal voltages. They need not be fully differential, correct? Is that correct? They need not be fully differential, and this is also something which you've seen here. So V1 is now 4.3 volt and V2 is 3.9 volt. VCM was how much? VCM was 4 volts. So your V1 is 4.3 volts, V2 is 3.9 volts. V1 is supposed to be how much? It is supposed to be equal to VCM plus small v1. V2 is supposed to be VCM plus
Okay.
small v2. And what is
VC.
VCM? VCM is 4 volts plus V1, and that is equal to 4.3, right? Similarly, V2 is what? 3.9 and VCM is 4 volts plus V2. So what is V1?
0.3
0.3 volts. What is V2?
minus 0.1.
Right? So you can
Yes.
clearly see V1 and V2 are not differential, right? They are not differential. They are not differential. This thing signals. So they will have a common mode and they will have a differential mode. So what is the common mode associated with V1 and V2? If I want to find out small VCM, what will that be? V1 plus V2 divided by 2, right?
Point one.
Yeah. And what will be VDiv? V1 minus V2 divided by 2. Am I right?
Yes.
Yes. Yeah. So now tell me,
So when the voltages are not fully differential, we have to do this process.
I mean, you need not do this. It's just done as was asked by Abhishek. I think Abhishek asked this question: why we need to split it into differential and common? It's just that we want to understand it separately. Okay, you can also take it. You can also try to do it in this manner: V1 and V2 separately. That's just your choice. It just turns out that if you split it into common and differential, the overall analysis becomes slightly easier and very easier for you to comprehend. Okay, otherwise you might end up making mistakes in the analysis.
Right. But when you just do this, you have a small VCM, and
uh,
that is your common mode signal, right?
Common mode, yes,
Then your
signals.
yeah, so then your total common mode signal will be VCM plus this VCM.
No, that's what. Now this VCM here is the bias voltage. This
Yes.
VCM small VCM is the common mode signals, incremental signal,
Okay. Okay. Okay.
and that is
Understood.
why I've specifically used this notation always. bias are always denoted with capital, all the letters capital. Okay, whereas this small signal is always denoted with all the letters as small. Okay,
Understood.
yeah.
Yeah.
So this is a small signal common mode voltage. This VCM here is the bias voltage, not the large signal. Please mind it. This is the bias voltage. What is the large signal in that case? What is the large signal if you say what is large signal? The total, okay, V1 and V2 here, these two are the large signals. Okay, large
Okay.
signal is
Yes.
the summation of bias plus small signal. Got it?
Yes.
Yeah, fine. Yeah, so this is BCM and V differential. Fine. Now, so now if I want to write V1 and V2 in terms of BCM and V differential, what will they be? So this is a small V1. What will be small V1? VCM plus V diff. Okay, and V2 is VCM minus V diff. Okay, so now you see
Yes.
that there are both common mode and differential mode signals at the input, and this is supposed to be a differential amplifier, right? So it should ideally reject common mode, but if it so that ideal condition should happen in some that ideal condition will happen in some situation. So that is why I asked you to take these two cases, wherein for the first one you assume that IB is ideal, okay, and the second one where IB is not ideal. That's an output resistance. So tell me, so differential, I am sure you will be able to find out differential gain. I am sure you will be able to find out. And in finding out differential gain, does this IB play any role, or let's say it has an output resistance here? Does this play any role in finding out differential gain?
No,
Why?
because the Vx would be 0 then.
Yes, Vx is 0 in the differential case, right? So this doesn't matter. Vx is 0, so this node actually doesn't matter in the differential picture. But in the common mode picture, Vx is not 0, isn't it? So there this node actually matters a lot. Vx is not 0 and what is connected here actually matters a lot. So let's call RO. RO is what? 20K. So the one case where this RO is infinity and the other case when this RO is there. So tell me what will be the situation. So if the RO is infinity, if this IB is ideal IB, what is going to happen to the common mode gain? So if you have applied any signal, small signal common mode at the input, what should be the small signal common mode at the output? So that is common mode gain, right? Because of the common mode at the input, what is the common mode at the output? That is the common mode gain. So tell me what is going to happen if your RO is infinity. Okay. So now if you apply a small VCM here, small VCM here, and small VCM here also, what is going to happen at the output?
Both is going to be same, and finally it will be
Yeah, yeah. So I mean, what will be the VOM and VOP? What will be the gain? A similar question you have already done, right? Okay, let me rewind it to this place. So common mode gain is what? It is a very strong function of the output resistance of the current source, right? Isn't it? Now in the case where RO is infinity, what is going to be the common mode gain?
Gm into RL.
Come on, man, how is that
zero.
Zero,
Oh,
zero.
sorry.
zero, right?
Okay.
It is going to
Yeah.
be zero. When
Yes.
when the output resistance of the current source is going to become infinite, the common mode gain is zero. And why does that make sense? If this I zero, if this is ideal I zero, ideal current source, the common mode gain is supposed to be 0. Why is that making sense? When do you expect a common mode gain in the circuit? So if you have applied a small common mode at both the places, not this circuit, yeah, this one, yeah. So if you have applied a common mode at this place and this place, at both the places, at both the inputs, you have applied a common mode, right? VCM. Now because of that, we know that a same amount of current is going to flow through, right? Same amount of small signal current is going to flow through both of these transistors, correct? Are you able to understand that?
Yes.
One second. Yeah. So I was saying that the same amount of current is going to same amount of small signal current is going to flow through both of these, right? So now, if VCM is rising, okay, you expect the current here to be rising, right? But the current will be rising in both of them equally, right? Right? The current should increase in both of them equally. Is that correct?
Yes, yes, you
Yes.
are correct.
Yeah. Now, if that happens, you see that if the currents rise in both of them equally, you see that the total current will exceed I0, right? The total current will exceed I0. The total current will no longer be I0 because earlier the let's say in some condition in the bias current was this one was I0 by 2 and this one was also I0 by 2. The bias currents were I0 by 2, I0 by 2, right? And along with this, with the application of this VCM, small VCM here, the currents are going to further increase, right? This will now become I0 by 2 plus some I1, and this will also be I0 by 2 plus some I, or rather let's call this I naught, small I naught, right? So you see that if there is an input VCM here, uh, if there is some input VCM, because of this, if this rises, if VCM rises, then you expect the current to also rise here, right? In both the branches, VCM will rise, so current also rises. So total current is now what? The total current that is going to flow through this node is what? It is I0 by 2 plus I0 by 2 plus 2 times small I0. So the current is now exceeding, right? But that is simply
Yes.
not possible because the current source at this the bottom current source is going to enforce a condition that the current cannot change here at this node. The current simply cannot change. It simply has to remain fixed at I0 only. So which means that common mode current I0 and I0 cannot flow in this particular situation, right?
Yes.
So which means that if the current is not flowing here, which means what? There cannot be any voltage change here, right? VOM and VOP cannot change because of any common mode signal at the input, right?
Yes.
So that is why we see that because of when the current source becomes ideal, the common mode gain from input to output also becomes equal to 0, because then the current source enforces a condition on the total current that is going to flow through. Always remember that whenever there is an input common mode signal, it tries to change the total current that is going to flow through the branches, okay? That will not be possible if the current source that is going to be present at the tail node is ideal. Fine. So the same case is here. Same case we have we have here, we have the same case here. If this current source becomes ideal, what do you think should happen to the overall common mode gain? If the current source here becomes ideal, what happens to the common mode gain?
Again, it will become 0.
Yes, it will become 0. So that is why in the first case, if IB is an ideal current source, because of this VCM, you should not expect any change in the output. Okay, the only change will happen because of this V differential. Got it?
Yes.
In the first case. But in the second case, where you have some IB, so where you have some R out of IB, that is you have an R out here. And that is equal to how much? 20K. So this, because of this 20K, now you can expect that this VCM, small VCM, will also cause a small incremental change in the output common mode. Okay,
Yes.
so try this out. I mean, I have already given everything that you need for this particular exercise. You know how to find out the common mode gain from input to output, and now you know how to find out. Now you also know what is the argument behind that. So try to do this on your own. We'll meet it in the next. We'll discuss it in the next class. That is going to happen. That will be the last class. Okay, by the way, on next Tuesday. So try to solve it by then. Okay, I don't think I don't have anything else to cover today. So if you have nothing else, I'll just log off.
Here, Mayank, one
Yeah.
doubt is there.
Yes. Go on.
For this configuration now, if I take the differential gain, that is going to be GM by 2 into RL, right? RL we have to consider 1 by GM, no? Because of
Yes. Yes. It's a
diode
diode connected.
configuration of.
Yes. Yes. It's diode configuration. Diode connected configuration. So yes, it will be 1 over GM4 and GM3.
Okay. Yeah,
Yes.
thank you.
Welcome. It's actually exactly the same as this particular exercise. Okay. It's just that R1 and R2 here are replaced with 1 over GM and 1 over GM3 and 1 over GM4. And the M1 and M2 are just P mosses instead of N mosses. That's all. Nothing else. Okay. Okay. Now let's meet again next Tuesday. Thank you. Thank you for joining.
Thank you. Thank you.
Thank you, sir. Thank you, sir.